Assalamualaikum everyone. Welcome to my video tutorial for high school physics students and enthusiasts. My topic in this episode concerns the temperature dependence of resistivity of most metallic conductors. What does the constant known as temperature coefficient of resistivity tell us about the effect of change in temperature on the change in resistivity or even the change in resistance of metals? We will find out. Just hang on, watch and learn. The question is, a platinum wire is used to determine the melting point of the element indium. The resistance of the platinum wire is 2.000 ohms at 20 degrees Celsius and increases to 3.072 ohms as indium starts to melt. Question is, what is the melting point of indium? The temperature coefficient of resistivity for platinum is 3.9 times 10 to the negative 3 per Celsius degree. For your additional information, the element indium is a post-transition metal with atomic number 49 and mass number 115. It is a soft silvery white metal occurring naturally in association with zinc and other metals. And these are the other data given in the problem. We have the initial temperature denoted by capital T sub naught equal to 20 degrees Celsius. We also have the initial resistance capital R naught equal to 2.000 ohms. And then we have the final resistance capital R equal to 2.072 ohms. Alright, the given temperature coefficient of resistivity for the platinum wire denoted by the Greek letter alpha is equal to 3.9 times 10 to the negative 3 power per Celsius degree. And our target variable is the melting point of indium, which in fact is the final temperature of the platinum wire denoted by capital T. Before we proceed, let us first recall your lesson on what you call drift velocity, right? So in this diagram, we are given the situation when the conductor or the conducting wire, for example, is not yet subjected to what we call an electric field. All right. So the path of the electron without an electric field, we say, is that the electron moves randomly. And the random motion of the electron is represented here by the zigzag or the green zigzag arrows. All right. For example, when the electron starts at point P1, all right, so it moves in that direction, all right, then it goes this way and proceeds that way, all right, until it reaches point P2, all right. So this random motion of each and every free electrons in the conducting wire when there is no electric field yet, all right, uh, is such a large amount of speed, all right. Now, what happens if there is now an electric field within the conducting wire, all right? So the path of the electron is now represented by, again, the zigzag red arrows, all right? So if you're going to trace the path of the electron with electric field, still its motion is mostly random, all right? From P1, it goes like that, downward, all right, upward to the right, then downward to the right, upward to the right, until it goes to point P2, all right, or P2 prime. So, although the path of the electrons, when there is an electric field, is still mostly random, but, all right, we say that the electric field results in a net displacement along the wire. So, in other words, um, each and every electron that is at random motion is also drifting, all right, drifting, or there is what we call a net flow of these charges, all right. So we can imagine the conductor with an internal electric field, all right, in this illustration, an electron which has a negative charge, all right, and the force on it due to the electric field, all right, is in the direction opposite to the electric field. So while the electric field in the conductor is directed to the left, the force acting on the electron is directed to the right, right? So this is how we imagine electrons as they move through a conducting wire that has an electric field, right? It results to what we call drift velocity of the electrons, which I'm sure is to recall in our past lesson or past video on current density and drift velocity. We said that, all right, for the electron to be able to travel a distance of 1 meter, all right, 1 meter in a given conducting wire, it, it would take 2 hours. That's how slow the drift velocity of the electron is, all right, when the conducting wire is subjected to an electric field. Now, how does this explain our present topic, okay, on the dependence of what we call resistivity as well as resistance of a conducting wire on temperature. Right. The resistivities of most metallic conductors are said to be temperature dependent. As the temperature increases, the ions of the conductor vibrate with greater amplitude, making it more likely that a moving electron will collide with an ion as shown in this figure. So this impedes the drift of the electrons through the conductor and hence reduces the current. All right. We also recall that if the current is reduced, all right, at a given electric potential, then we say that um, the resistance, all right, the resistance is also affected. In other words, at high temperature, the resistivity is increasing, okay, because they are proportional to each other. Over a small temperature range, that is, up to 100 Celsius degree or so, the resistivity of a metal can be represented approximately by the equation. All right, rho at a certain temperature, capital T, is just equal to rho naught, where rho stands for the resistivity. All right, of conducting wire. In this problem, we're talking about platinum wire. Rho naught is the resistivity of the same conducting wire at a certain reference temperature. All right. The reference temperature taken is usually 0 degrees Celsius, or in this problem, we are using 20 degrees Celsius as the reference temperature. All right. So this rho naught will be multiplied. Okay. This will be multiplied by the value of the quantities inside the bracket. All right. So inside the bracket, we have here 1 plus alpha. The Greek letter alpha represents what we call the temperature coefficient of resistivity of platinum wire, which has to be multiplied first by the temperature difference, capital T minus T naught. And their product will then be added to the constant 1 before their sum will be multiplied to rho naught. All right. So whatever comes out as the product will be the resistivity of the material at that final temperature, capital T. But in this problem, our target variable is the final temperature, capital T, which incidentally is also the melting point of the element indium. So we need to isolate capital T and come up with this working equation. That is, capital T is equal to T naught, that's the initial temperature, all right, or the temperature of the reference value, which is 20 degrees Celsius. Then add to that the quantity inside the bracket, all right, where 1 is to be deducted from the ratio of rho over rho naught. And then the number inside the bracket has to be divided by the constant alpha before the whole thing inside the bracket divided by alpha will be added to T naught. That is how we go about determining the final temperature, capital T. All right? All right, so moving on with our solution, we said that the Greek letter rho is the resistivity of the conducting wire, which is platinum in this problem. All right? That is the resistivity at the final temperature, capital T. All right? Now, this constant value for rho, all right, can be expressed as, or is actually equal to 3.072 ohm meter. All right. While rho naught, which is the resistivity of the same material at a reference temperature T naught, and that rho naught is equal to 2.000 ohm meter. Right? How we obtain these values for rho and the rho naught is actually based on the formula for the resistance big R. All right? The resistance big R is just equal to the product of rho, or the resistivity of the conducting material, multiplied by the length of the conductor divided by the cross-sectional area, capital A. All right? Now, in this problem, the ratio of the length over the area, or cross-sectional area, is in fact constant. Why? Because we are using the same what we call length of platinum wire. When this given length of the platinum wire gets heated, all right, we assume that there is no what we call appreciable or significant change in its length, neither does its cross-sectional area changes. All right, so capital L over capital A is assumed to be constant. Therefore, we can just set the resistivity rho to be equal to the value of R, all right, meaning the rho value is just equal to the numerical value of the resistance, which actually is given in the problem. All right, so with L over A being constant, it follows that the resistivity rho, all right, is just equal to the resistance big R. And that is the basis, all right, the basis for getting the value of rho at that temperature capital T. Alright? Notice that the unit of rho is ohm meter. Rho, rho naught is also determined using the same relationship of resistivity and resistance. Alright? Which is also equal to 2.00 ohm meter. Alright, so using the working formula to find the final temperature capital T, alright, which is T equals T naught plus bracket quantity rho over rho naught quantity minus 1 bracket divided by alpha. Alright, so upon substitution of the data, that is T naught, which is 20 degrees Celsius, plus, all right, bracket quantity, the value of rho, 3.072 ohm meter, over the value of rho naught, 2.000 ohm meter quantity, minus 1, then you have the bracket divided by the value for alpha, 3.9 times 10 to the negative 3 per Celsius degree. And doing our math or simplifying, okay, so we are showing here the step-by-step simplification, all right, the result of um, dividing, all right, or getting the ratio of 3.072 ohm meter by 2.000 ohm meter is given here as 1.536. All right. The ohm meter unit cancels out. So 1.536 minus 1, okay, becomes a unitless number. And that will be divided by the value of alpha, 3.9 times 10 to the negative 3 per Celsius degree. All right. And simplifying further, we get the value of T naught, which is 20 degrees Celsius, plus 137 Celsius degree. That's the result of getting the difference, all right, between 1.536 and 1, then dividing that by 3.9 raised to the negative 3 per Celsius degree. That's how we got 137 Celsius degree, which when added to the initial temperature T naught, we will get the computed value for the final temperature capital T equal to 157 degrees Celsius, which we said is also the melting point of the element indium, which is the target variable in this problem. So before we end, here is the key concept applied in this problem. We say that the resistivity of a material depends on temperature, and so does the resistance of a circuit element made of that material. Over a small temperature range, the change in the resistivity of a metal is approximately or nearly proportional to the temperature change. So that will be all. Till the next episode, inshallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.